sometimes with these flow chugs, if you know just what equations out there are possible, it actually becomes pretty easy, right? You got P equals IV. That's the base power equation. Power equals current times voltage, right? Then there are two others that if we combine that with Ohm's law, V equals IR, that you can get, and I'm not going to get that for now. I actually want to work it long ways, and I'll put those up and point it out here in a second. For number one, what is the resistance of a light bulb when connected to a 120 volt power source draws 60 watts of power? Well, why don't we do this? P equals IV. That's 60, and I did put a decimal after it, so 60 exact, right? 60 equals I times 120, right? That's going to give me current. What's the current? Don't have to use your calculator. 0.5 unit. Oh boy. Amps. Thank you. 0.5 amps would be the current, right? Then that allows me to plug into Ohm's law. V equals IR to be able to solve for the resistance, right? That's going to 120.
Why don't you just do P with P squared over R?
We're going to do that. I'm going to show you that next. R equals 240 unit, please. Ohms, right? Now, AK referred to a couple of other equations here. So I've got these two equations, what I just used. Yeah, but if we combine these guys, you got P equals I squared R in one derivation. All we did there is we used Ohm's law, right? That's V equals IR. Plug the IR in for the V. You know, you took these two guys and plugged in for the V. Okay, that's where the I squared R comes from. The other one, P equals V squared over R, right? I simply reversed it. I solved this Ohm's law equation for I, right? So I equals V over R. Plug that in for I, okay? So you end up with V squared over R. Okay, so if you wanted to, you can have those two equations written down on your equation sheet. You don't even have to do a two-step flow chart. It's just stick in, pop out the answer. Okay, that's fine. Next step here. It tells us the length of wire, and it asks us and a radius, and it asks us what's the light bulb made of. Now, the resistivity of each material is unique, right? Each material's resistivity is constant and it's unique to that individual material. You figure out what the resistivity is, you look in a table in a book, you find out what material is. So we're solving for rho here. So let's use R equals rho L over A. Okay, R equals rho being resistivity, length of the wire divided by the cross-sectional area. Now, wires are generally cylinders. That means the area is what?
Pi R squared.
Pi R squared. So this becomes R equals rho L divided by pi R squared. I'm going to solve this around with just letters for now, if you don't mind. I'm looking for rho, right? So that's going to be, rho is going to equal pi, big R, that's an L on top, pi, big R being resistance, little r being radius squared, divided by the length of the wire. Be okay with that? I mean, just moving around letters?
Okay. Yeah. When you do with numbers, can you just find L over pi R squared and then just divide that by resistivity?
Yes. Let me come back and do this. Let me come back and try to do this again and help us understand this. Let me work this in different steps. You need to be okay with working with letters, just for, especially those of you who are looking to do something in the field of science or math, right? You're going to end up working a lot with just letters, okay? So get okay with it. Those of you taking AP Chemistry next year, from what I hear, Mr. Byers refused to plug in numbers early on. He likes to work in letters if he's got long algebra. Okay, that's just what I've heard. Lots of times, AP chemistry probably is long as also. So you end up getting numbers quick. But I'm looking for rho. So let's multiply both sides by pi little r squared. Okay, that's good. Okay? Now divide both sides by L. Yeah? That's all it is. So I've got big R for the resistance here, right? And then I've got pi radius squared down there, right? So I multiplied everything in the denominator over to the other side. So now I got my pi radius and my resistance being multiplied. Oh, it can be pi big R squared. It can be R pi R squared. It can be whatever order you want, right? Just like 2 times 3 times 3 is the same thing as 3 times 2 times 3, which is 3 times 3. You know, who cares, right? Tyler.
Can you solve for L over pi r squared and then take that number and divide r by that?
Yeah. That's a just fine algebraic step, right? This is just me solving for you, just so I can plug numbers in, right? The advantage of this, doing it this way, now I just plug in pi. What I said the radius was up top, so I don't have to scroll up, please. 1.47 micrometers. 1.47 times 10 to the negative 6. Micro means negative 6. So micrometers, negative 6 meters, right? 4.17 times 10 to the negative 6. The resistance that I solved for up there, please give me that. 40. All divided by the length that I gave you up there.
They should be the r squared.
Thank you. 0.029. Now, why 0.029? It was good. All the way up here, I said 29 or 2.9 centimeters. Centa means times 10 to the negative 2. You can either jump the decimal twice like we did, or you can say times 10 to the negative 2 on it. Don't care which. Right, and so now that there's nothing except take this and shove it into calculator. 5.61 times 10 to the negative 8, you look in your book, and it is tungsten, right? What filaments and light bulbs actually are made of. Tungsten.
You even need to solve for that.
I'm sorry?
You literally need to solve for what element it is.
Yeah, well, you know, I could have changed it up on you. Something that I want you to notice from these calculations, how thin that filament has to be to make this work. How thin that filament has to be. I used all realistic numbers, right? I mean, scrolling all the way back up to the top, 120 volts is what comes out of your walls. Now, granted, these equations, we're dealing with more direct current, and what's coming out is AC current. We'll talk about that later. 60-watt light bulbs is the average light bulb that you plug in, right? 60-watt light bulbs, the normal light bulb. That means the resistance of that light bulb is generally about 240 ohms, and we solve through with, 2.9 centimeters. That's a reasonable length, for a filament inside of a light bulb, somewhere in there. Okay, that's a reasonable length. Meaning to get tungsten, it has to be in the order of micrometer thin. Very, very thin for this to work. Okay, very, very thin for this to work. All right, any questions? Okay, now, let's just work a couple simple ones, then we'll start working a few more complex ones. Sorry. Yeah, well, okay. A couple of simple ones. Find for me, please. Never mind what the battery is, right? Please find for me the resistance right now on your own sheet of paper, and the equivalent resistance for the following circuits. 2.5, 3.7 ohms, 4.9 ohms, and let's keep all of them the same here for a simple parallel. Let's say 2.5 ohms, 3.7 ohms, 4.9 ohms. All right, that'll take you what, like 2 minutes most? Now, first one, all in series. How do I find the equivalent resistance? Add them all. I don't even think we need to go over that. What does the equivalent resistance come out to be? 11.1 ohms. I have a problem with your number. What's my problem with it?
11.
Sig figs.
Sig figs, it needs to be 11, right? So 11 ohms, right? 2 sig figs, 11. Now, let me take that back. We don't deal with this much. Let me take this back a little bit and say it's actually not going to matter. You can just use 11 there. I haven't ever taught you sig figs with adding. Never have I taught you sig figs with adding because, quite frankly, it's unnecessary. I don't have a single physics equation that only involves adding. There is some multiplication and division in it, right? And that rule always presides. If all you're doing is adding, like in this case, the rule isn't keep just the fewest number of significant figures, it's keep the fewest number of decimals, right? So the correct answer here with sig figs would have been 11.1. The reason I'm still saying it's not going to matter is because we're going to do something Monday with that 11.1 that's going to involve multiplying and dividing, Ohm's law, right? So we're back to kind of canceling all that back down. Anyway, the technical answer would have been 11.1. Now this one down here, just a common mistake ends up being made. So let's go over this. This is 1 over R EQ, equivalent resistance, or RT, total resistance, or whatever else you want to call it, indicating all the resistances added together. Right, gentlemen? That's going to be 1 over 2.5 plus 1 over 3.7 plus 1 over 4.9. Now, the most common mistake that happens is everyone plugs that side into the calculator, right? And whenever you plug that side in the calculator, what do you get? 0.874?
Yeah.
That's not the answer. I've got to take the inverse of that. I figured out what 1 over REQ is, right? I've got 1 over REQ equals that. Most common mistake, and I promise you someone's going to make it on the test this unit. Swear to you, okay? It's never failed. Doesn't matter how much I emphasize it in every single class. I'll say it time after time after time. Someone will make that mistake on the test. I hope it's not you. Make sure it's not you, okay? Someone on the test will forget to take the inverse at the very end whenever it comes to parallel, right? So you take the inverse of that, you get REQ equals what? 1.14?
Yeah.
1.1415 ohms. Now, let me come back and talk about this stuff in general. Let me come back and talk why this is useful before I go into complex things and give you a few heads up on this. The idea here is we're going to use this equivalent circuit thought to take very complex circuits and simplify them down into the most simple circuit possible. Battery or a power source and one resistor. Okay, like I have drawn. That's what an equivalent circuit is. It's a circuit that behaves the exact same way. It has the same total resistance as if you had all the little pieces in there, except it's just one thing, right? Instead of looking at all the pieces, you look at it holistically, right? So you don't have to worry about all the little nuances inside. It makes it a lot easier to deal with. It's kind of like, think about all the different things we have going on in the school, right? Power-wise, how many computers are there, how many lights are there, how many, so on and so on. But instead of looking at all the different little things, trying to figure out the current, the voltage inside each one, which we're going to do doing things like that. Instead of going through all of that, instead, equivalent circuit, that's like the power guy simply walking out to the lines that are going into the school, saying, I don't care about what's inside, all I care about is what's happening with the power lines going in. I'll treat the entire school like one big resistor. That's the equivalent resistance. Okay? And that's the idea here, to be able to figure out what it is to simplify it down. Also notice something for me here. When in series, the resistance will always come out greater than any of your other resistors. Heck, you're adding, not done, right? So it's always going to come out greater. Here's the one that might not have seemed completely logical. In parallel, the resistance will always come out less than any one of your input resistors. I'm doing the inverse of them and doing the inverse of it again. But mathematically, you don't do that much, right? So you might not have realized that. Whenever you're doing this mathematical principle, my smallest resistor was at 2.5 over there, and my total resistance actually went down. In fact, the more resistors you add, the lower the equivalent resistance will become. The more resistors you add, the lower the equivalent resistance will become. I don't care if you slap in a 100 mega ohm resistor in parallel with those guys. It might not drop the resistance much, but it will drop it a little bit. It'll drop it a little bit. Think, if you will, to Walmart, your favorite store, right? Walmart, yeah. So you're going to go to Walmart, right? Now, Walmart, depending upon the time of day that you're going, is either great or it's a nightmare. If you're like, if you've been to Walmart, I don't know if the Walmart here is like the Walmarts in Athens, but in Athens, if you go to Walmart Sunday afternoon, it is terrible. I mean, it doesn't matter. There's never enough lanes open. You're going to wait in line forever. It's just like half of Athens decided, let's go to Walmart, and they all went to Walmart, right? So think about, if you will, with Walmart, each resistor here is a cash register. Each resistor is a cash register, okay? And so in the picture I have drawn, there are 3 lanes open, right? Now, resistance, like total resistance, is kind of with the idea of how long it takes you to get out the store, right? How long it takes you to get through, okay? If I open up another cash register, right, will it, in parallel, because that's how cash registers work, right, they're in parallel to each other. If I open up another cash register, will it ever slow things down? No, it will only speed things up. It'll only make it easier to get through. It'll lower the resistance. Even if we put poor, bless her little heart, Granny, right, on that cash register, who looks at your credit card and goes, your debit card, goes, what's that? And doesn't have any idea what, and swipes it the wrong way and has no clue. Even if she's incredibly slow, that's a very high resistance, because another cash register opened up, the overall resistance of the store went down. You're able to get through easy, right? That's why the equivalent resistance here in parallel will always come out to be less than all of the other cash registers, right? For all the other resistors, every single time. Got it? Okay. Now, let's talk about more complex circuits. Circuits that have series and parallelism. Circuits that have series and parallelism. Let's start out small. I want to find the equivalent resistance of that circuit. I want to find the equivalent resistance of that circuit. What do I do? They're not all in series. They're not all in parallel. Do them separately. Do them one at a time. What do you want to do first, series or parallel?
Parallel.
It does matter. It does matter. Here's my advice to you on this. Always start with the most obvious. Because if you do them in the wrong order, you will get this wrong. Okay, if you do them in the wrong order, you will get this wrong. Start with the most blatantly obvious ones. And for the most part, the most blatantly obvious ones will be the ones located the farthest from the battery, the farthest out. Okay, start with the most blatantly obvious ones, the ones that are like the picture-perfect definition of parallel or series. Okay, where there is no confusion, there is no doubt, most of the time it will be the farthest away from the battery. What's the most obvious ones in this picture? The two parallels. The two parallels, right? If you tried to say, well, what about this 2 and 3? It's in series. right? I'd say, well, yeah, but is the 2 in series with that 3, or is the 2 in series with the other 3? What do you do first, right? Yeah, it looks like it's in a loop there, but maybe this is the outside loop we should pay attention to, and then there's just a shortcut Y, right? This is not a good picture of series. The parallel out there is a perfect picture of parallel. Start from the farthest out. So first step is going to be to reduce this entire circuit down, to look like this. Here's the 2. And this resistor right here is going to be the combination of those 2 other resistors in parallel. So I got a half, right? So this is 1 over RT equals 1 over 3 plus 1 over 3, right? So that's 2/3. So RT comes out to be 1.5 ohms. Okay. So this tells me this is 1.5 ohms. I took those 2 parallels and I reduced them down into a single resistor. Okay? I'm working step by step by step. There's only one more step left. Those 2 resistors, parallel or series. Series, textbook, right? So to get to the equivalent circuit here, I just need to add these guys. 2 plus 1.5 gives me a 3.5 resistance. There. That's your equivalent resistance of that circuit. 3.5. So you work in steps. All right, let's give you. Right. If you did a series first, you look at things would come all on. All right, let me give you a little bit more complex one that I'm going to let you work right now. Do I need to leave this up for a second? Yes. Okay, I'll leave it up for a second.
Actually,
Fire away.
okay, so I understand you do the series first. Can you spell it?
What?
Okay, those are the things. Great, you take the inverse of both of those, and you add them.
Yep, doing the parallel first.
I did that, and then that gives us 1.5.
Correct.
And where do we put the 1.5?
Think about whenever, it's a good question. Think about whenever you're combining resistors, think about smushing them together. All right? Think about taking the 2 resistors and just, if you will, here's a good solid word, mashing them together, right? You're going to mash those 2 guys together, smush them together, right? So take these 2 guys, smush it in, right? Smush the 3 into the other. So it becomes in the same line now as the 2. I mean, the 2 separate wires cease to exist, right? Now there's only 1 wire. If it helps you think about it, I took this outside 3 over here, right? This outside 3, and smushed it into the next 3. Okay? Yeah, and then you write your 1.5 in place of where those 2 3s were.
And then add them, and get 3.
Correct. Correct. Then I take this guy and the 2 up here and I smush them together to get me just 1 resistor over there. Okay. All right, let's run a little bit more complex one. I'm going to let you work. Let's have a little bit of fun here with it. I'm going to hit you with a diagonal, and I'll talk about that here in a second.
Okay.
Start.
Yes.
Okay. 2, 4, 3, 2, 5, 2, 2. All whole numbers measured in ohms. Now let me talk about diagonals here for a second, just to clarify. My recommendation to you in diagonals is to try to straighten them. My recommendation to you with diagonals is to try to straighten them. Okay? That means that just like you can physically kind of grab wires and move them around, right, as long as you don't mess it where they're connecting, do the same idea here. What I mean is, imagine, do I need to give you a second to copy this down?
Yeah.
All right, I'll give you a second to copy. Here's what I mean by straightening the diagonal. You're allowed to grab wires and move them, so to speak, mentally in your mind and then redrawing them, as long as you don't violate these two rules. Don't cross another resistor. Don't cross another resistor, right? And don't cross another junction of wires. Don't cross another resistor, right? That means that I can't take this guy past the 2. There's the limit where I can slide him, right? And don't cross another junction, meaning I can't slide him past there. I have to slide in between those two locations. Okay? Oh, we can stretch things too. I'll get to that. This guy, I can slide anywhere between those two, right? But I can't do anything else except slide. So what I'm going to do is I'm going to slide straighten this. To make this picture look something like this. Let's see, 2, 4, 3. Two, 5. Two.
I can cheer.
2. You see what I did there? I straightened it. I straightened it out.
Stretched it also.
I stretched the wires a little bit too to make it work. I gave myself some more space. This diagonal right here became that one over here. Now it's vertical. Now it's vertical, right? I didn't violate any rules. The junction still is between the node, or this junction still between the other junction and that resistor, and still between those two resistors. Okay? So that 2 is going to be parallel to the 2 and 5 that are in series, right? So find for me the equivalent resistance of this circuit. I recommend working outside in. So for example, what are the 2 resistors you want to add first? 2 and 5 in series. In series. Okay, so add the 2 and 5 in series. You're going to end up adding that to the 2 in parallel. You're going to add that to the other 2 in series, and so on and so on. Walking through this. Now, here's what's happening. I've got the original circuit. I need to figure out what I need to add first, which we had already all agreed on needs to be the 2 and the 5, the far outside. They are about as textbook series as you can have. Right? You can add almost anything you want together, but you have to follow the rules. And the problem is, lots of these resistors right now are kind of in between the rules. For example, you look at the 4, the 3, and the 2 over here, and you go, they kind of look like they're in series, but are they really? Right? There's other wires coming out from these guys. The definition of parallel is current can divide, and the current divides after the 2 into all these other little branches before it gets back around to the 4. And not the same current goes through the 2 as through the 3. That's one of the definitions of being in series. So that doesn't exactly work too well, right? You could try to figure it out and everything else. Trust me, it's not really going to work, okay? Instead, go with the simplest thing possible, where there is no debate. It almost always occurs as far away from the battery as possible, okay? So go to the far ends of the circuit, right? If it's kind of a long one like this, go to the long end. If it's just kind of fat and square, go to the exterior of it, okay? And then gradually work your way in. The 2 that are the most obvious, that there aren't any debate about, are the 2 and the 5 over there. So whenever I'm going to redraw this thing, I get this. Everything else stays the same. Everything else stays the same except the 2 and the 5. The 2 and the 5 now become a 7. Now become a 7, right? I'll work the next step, and then I'm going to turn it loose to you. The 2 and the 7 now are the next most obvious. What are they in? Parallel, right? And so I'm going to redraw the entire circuit, taking the 2 and the 7, putting them in parallel.
Oh, wait. Then you have this one 7, right?
Pause. Where are your hands?
Somebody.